Perfect. Okay, thank you very much for the nice introduction. I think I have -2 minutes for my talk. I will try to make it short, since you already explained a lot of the concepts very nicely in your talk. So my name is Doménech. Most of you know who I am and who we are. I come from Photonics. I'm the CTO for this spin-off company here at the Technical University of Valencia. And I will briefly describe our activities in the project Fix for Life, which is this one here. And it's basically focused on silicon nitride photonic integrated circuits for life science applications. So I will shortly introduce the company, Photonics. Later on, I will pass fastly through this photonic integrated circuit explanation, which already did Pascual very nicely, to focus on the actual project Fix for Life, which is an H2020 pilot line. I will briefly describe what it is. So who we are a spin-off company of this very university. We were founded in 2011, so we are already 7 years almost there. And we have our headquarters here in Valencia, but we have also presence in the United States, Netherlands, and China through our commercial representatives. So we are currently 11 members of extensive academic and industrial experience. But even though we were founded in 2011, we all come from academia mainly, and so we have been in the field of integrated optics more than 12 years. So we are located in the campus here at the Business Development Center, which is 200 meters away from this location. So what is our activity at Photonics? So we mainly provide full services for the development of application-specific photonic integrated circuits. So we are mainly mimicking the CMOS fabless model of the electronic world. So we position ourselves as a design and also as a test house, where we take a system concept, we do design of a chip, and we handle the manufacturing and packaging through generic foundries who offer generic processes as well. So this is what we call the circle or cycle of life of photonic integrated circuits, which summarizes the activity at Photonics. So our customers can, there's something weird here, can come with a system concept. So we help them on this feasibility stage on translating this concept into an actual optical architecture, choosing the most appropriate integration platform, like the ones that Pascual showed, indium phosphide, silicon insulator, PLC, you name it. So we can later on build a chip architecture which is translated onto an actual chip design or a layout. By using our software tools, we can do this performance simulation, the mask layout and the design rule checks that must be accomplished in order to be manufacturable. So we send it to manufacture through our network of external foundries. And later on, we can do the bare die or bare chip testing here in-house. And we can also handle the packaging itself of the devices. And a final stage that is not here, but we can also do the test of the packaged devices here. So you see this whole cycle of life of developing a photonic integrated circuit can take up to 1 year in most of the cases. So we try to provide this total flexibility so you can enter at any of these stages. So if you have capabilities for doing the design yourself, we can help you out to handle the manufacturing or either the testing or the packaging or whatever the stages you can choose here. Or provide the turnkey solution, so the full cycle. So this is mainly our introduction. So I will go fast through this section, which already Pascual lectured very well to you all. So why integrated or integrating a system? So you know optical systems are also bulky, big, and can include lasers, fibers, waveguides, or modulators. And so the main idea is or why using photonic integration is to miniaturize these complete optical systems into a single photonic chip, which mainly or lately will be packaged and used into a more complex system. So the advantages of photonic integration are pretty clear. So you can reduce volume and weight, but you can also have simpler assembly and packaging. Depending on the application, you may look for better mechanical and thermal stability, or maybe you want to scale up your devices, which in the end allows you to scale up also in production. And eventually, what you would like is to reduce costs when you go for larger series. So why peaks for visible light? As Pascual said before, basically the largest market, or the market that was pushing forward this technology, was the telecom, where they were working at the infrared wavelengths centered in 1550. However, for historical reasons, the biochemical and medical applications usually work at lower wavelengths. So for a number of reasons, maybe one of the main reasons is that the cells do not suffer at these wavelengths. So photonic in general in life sciences have been used since a lot of years ago to burn, to cut, to ablate, and to diagnose, to illuminate and measure things. So for instance, these applications already use photonics in general, laser surgery, endoscopy, microscopy, tomography, ophthalmology. But all this has been using bulk photonics. So where these photonic integrated circuits have an application field. Pascual already showed these diagnostic devices, or point of care, and lab on a chip, with a nice example from Professor Laura Lechuga. But also there are other fields that these photonic integrated circuits can be applied to. For instance, in microscopy and cytometry, in healthcare and biochemistry, DNA sequencing, and embedding them onto medical instrumentation. So now focusing on the technology that I will show later on, that we are using in the Peaks for Life project. The silicon nitride is a good candidate, or is an excellent substrate material to build photonic integrated circuits for visible light for the reasons that Pascual already gave. So it has a low propagation loss at this wavelength. And also it's important they can be processed using standard CMOS processes like in electronics. So let me give you a brief introduction to the pilot lines H2020. So this project, Peaks for Life, is one of these pilot lines. Mainly the pilot line is a research program funded by European Commission in the H2020 framework program. The aim of these pilot lines is to bridge the gap between R&D and industry production. So in order to provide pilot production of, in this case, photonic integrated circuits for certain applications. So far, there are 4 that are already running. So the one I will describe in detail, which is this Peaks for Life, which is silicon nitride photonic integrated circuit pilot line for life science applications in the visible range. There's another one which is called PI-Scale, which is the aim is to bring flexible organic electronics to pilot innovation scale, mainly based on OLED technology, organic LED technology. Then it's the MIRFAB, which Pascual already mentioned, which is the mid-infrared photonic devices for chemical sensing and spectroscopy applications. And the later, we started the last year, is the PICS app, which is a pilot line devoted to provide photonic integrated circuits assembly and packaging. Okay, so this is Peaks for Life, again, developing photonic integrated circuits for life science applications. We are 16 partners from across Europe, maybe you know some faces in the picture. And the idea is to build a unique pilot line capacity and open access, this is important, open access services for silicon nitride visible photonic integrated circuits. The wavelength range we are targeting is from visible to near infrared almost. So these are mainly the partner roles. So where each of these partners are located at. So we have software and design companies like Lucida, Phoenix Software, and VLC Photonics providing this design. There are manufacturing partners like IMEC, Lionics, and Soulmates. There are other partners that provide only device test and packaging, and some partners which are the application partners, which provided an idea or concept that we will do a demonstrator. I will talk by the end of my talk about these 4 demonstrators that we plan to develop across or along the project. Sorry, just give me a second. In this project, there will be involved 2 platforms providing silicon nitride manufacturing capabilities. So one is the one from Lionics, which Pascual already mentioned briefly, with their proprietary silicon nitride process, which is called triplex. The Lionics is a Dutch company, and IMEC is from Belgium. They provide their what they call BioPix platform. The goal of this project is to provide open access to multi-project wafer runs, which basically consists on sharing the area on the wafer space, so in order to basically reduce cost at a cost of getting a limited number of chips. So we aim to have a periodic schedule of these runs, but we also plan to offer dedicated wafer runs if needed, on demand. In brief, the 2 platforms, there are, I don't want to enter into too much details of this, but the main difference between the IMEC or Lionics platform is that the IMEC provides PCVD silicon nitride, while Lionics is providing LPCVD nitride. So the IMEC one gives a bit more propagation loss compared to the Lionics. Also, both platforms plan to offer this cladding opening, so removing the cladding selectively in order to provide biosensors. And both have different options for coupling light in and out of the dies, of the chips. So you have the details, maybe you will get after this the presentation, so you can check on detail the specifics of each platform. Basically, the triplex, as Pascual said, they will provide, or it's in the plans to provide, for instance, a different tuner rather than the typical thermo-optical tuner. They plan to include piezoelectric materials to include modulator capability to the platform. So main difference between triplex or BioPix is the lithography tooling. In triplex technology, the lithography tool they use will allow us to have a minimum feature size of 600 nanometers, while the more advanced tooling equipment I have at the clean room of IMEC will allow us to have minimum feature sizes of 150 nanometers. So there will be, as I mentioned before, regular or ideally scheduled MPW runs across the year. Each of them, all this information will be provided and with details at the website of Pix4Life, which is www.pix4life.eu. And ideally, the users, the European users, will have a discounted price access, and the academics will have a larger discount. So for this year, there are 2 runs planned already that may incorporate external users, different from the partners of the project Pix4Life. So I showed briefly that there are other 4 pilot lines or 3 pilot lines additional. So we are working together with the Pix app pilot line, which provides packaging services on demand for the users of this Pix4Life platform. Also within the consortium, there are partners like VLC Photonics or Lionics that can offer characterization services on demand for these external users who want to access to the manufacturing capabilities of Pix4Life. So there are 2 partners that provide software in this project. The first one is Lucida software. So they will provide this functional circuit design, layout, the typical tools that some of you are attending to the training that it's taking from Wednesday to Friday here in Valencia. You will see some of these tools. And ideally, we want to build on top of these softwares a PDK. So either in Lucida or in Phoenix software. They have different, similar tools, FTTD, BPM, propagation and circuit design. And the idea of these PDKs is to compose or to gather the building blocks, elemental building blocks that are developed by the partners in the project to be offered to the external users, either for triplex or for biopics. So these PDKs basically will consist of a design manual where the technology will be explained, all the materials, waveguide cross-section, die templates, etc., etc. And, as I said before, a library of building blocks that we are co-developing among the partners of the project, where the users just can take all these building blocks and pick and place them on their own circuit. So also, they can use of the design assistance of VLC Photonics. We have a large experience working with Lucida or Phoenix software, and we can provide this consultancy design for non-experienced users, but also for experienced designers. And we can also develop custom building blocks for any specific application. So as I said before, and to conclude my talk, there will be 4 application demonstrators from 4 of these partners, and in the project. Mainly, they are so-called a flow cytometer, an OCT imager, and gas or bio multisensor, and a multispectral light source. So the first one that is being developed on the project is Bytoptica. It's a German company that produces laser engines, so multi-wavelength laser engines in the visible wavelength range. So basically, I don't know if you can see the details here, but this part here is a chip that combines, in this case, 4 different wavelengths from lasers, from red to violet. And it's being developed in the triplex platform, so this is a triplex chip. And why the use of this, or why integrating this multispectral light source? So there are 2 reasons. Their system is very, very bulky. They have motorized engines, so to align or to couple light from these individual lasers into a single output fiber. So that is costly in the assembly and also is unstable in its recalibration. And secondly is because it will be used for the second application. So there's another company in the consortium which is called Miltenji Biotech. Mainly they want to develop a flow cytometer. Cytometry is a technique employed in the biophysical sciences. Basically, it's about cell counting, sorting, biomarker detection, protein engineering. So basically, you have a stream of cells suspended in a fluid and passing them through a small pipeline and shining light on them. They can use they can make this cell sorting and counting. So they will use this multispectral light source developed in the project to build their flow cytometer. So the third application is from Bosch, the German company. So they are the most secretive. I cannot give many more details for confidentiality reasons, but they want to develop sensors, basically biosensors for market, for large markets. So for bio wearables. So they don't give too much details. And the ideal is like, as Pascual showed before, to have a set of sensors here based on Mach-Zehnder interferometers or ring resonators. They will functionalize this surface and to have labor-free detection as well. And last application is a Spanish company. I don't know if they were here last year. It's called Meldumix. They are located in Madrid, and they are part of the SECFO cluster as well. So they are building equipment for optical coherent tomography. this technology or this application is mainly is a diagnostics tool for imaging of, ideally their first prototype is for eye imaging, but they are developing systems also for coronary artery disease and dermatology. So this is the current bulk solution, so you can find it in a hospital. And they have developed, this is already a product. This is basically handheld equipment where you can have imaging of the skin or the eyes with a depth of penetration of 2 or 3 millimeters, but with a resolution or accuracy or in the range of micrometers, which is a very nice tool. So they are developing this in the IMEC platform, so you can have a single chip acting as this interferometer, which will be, if you build it in a bulk system, it will have a rack side. And this is all I wanted to show about the Pixel Life project. Thank you very much. Any question?
Thank you, David, for your presentation. Any questions from the audience? Okay, let's thank the speaker again.